In this video, we're going to look at our logistic growth model. We're going to look at its foundations, and then we're going to study its solutions and properties of those solutions. The logistic model is typically applied to population growth, though you can also see it in disease modelings, places where some element spreads through a population, but there's a maximum possible value that the infection pool or the population can reach. The idea is that it captures that idea that the growth slows down when you're reaching some kind of capacity level. We call that capacity level the carrying capacity and give it the letter L as a designation usually. And the idea is once we reach that population, we should stabilize. The way we get to there is in the logistic model. We assume that the rate of growth of the population, that would be dp dt, is proportional to the product of, is proportional to, equals a constant times, the product of the population now, and the gap between the current population and the carrying capacity. Well, that is a differential equation that practically writes itself just by taking those words, rate of growth of the population, proportional to equals a constant times. The product of simply means multiplication of those two expressions. That's it. There's our model from the words describing the scenario. When we worked with this differential equation before, we found that the growth rate, dp dt, was maximized at the population that was halfway towards the limiting population. It was argued that we could say that it's highest there because we're not close to the carrying capacity. We're far from the carrying capacity, which slows down growth, but we also have a lot of population to work with, half as much as physically possible. And so that's the sweet spot between having zero population, so zero growth, or being at the carrying capacity, L. When we get close to those two bounding populations, we found that the growth rate was very small. In fact, we can formalize that a little bit by looking at equilibrium levels, which are populations that remain constant over time, populations that if you start there, you stay there forever, which translate to populations which satisfy constant means zero derivative, and we can use our differential equation, this part here with our derivative being set equal to zero. That leads immediately to p equals 0, or if we look at this expression, p equals L are both equilibria. And again, those are entirely reasonable. If we start with zero population, the population stays at zero forever. And if this population starts at the carrying capacity, it also stays there forever. That's our informal definition of the carrying capacity, a population that can be sustained indefinitely. What about in between though? If we look at populations between 0 and L, and we look at our differential equation, what can we predict from that? If p is between 0 and L, then what that means is p is less than L, that's the key thing. So L minus p, big minus small, is positive. If we look at all the ingredients, this term would be positive, this term is population, it's positive, and we'd have a positive constant here. If that's the case, then we'd expect our derivative to be positive as well, and that implies population growth. You may see some practice problems where that isn't the case, but that would be the default assumption for a standard logistic model. If we're below the carrying capacity, then we have room to grow, and so we would see population growth. However, if we have a population above the carrying capacity, p is larger than L, then we have this difference of smaller minus larger is going to be negative. And if that's the scenario, we're going to have our differential equation written out here, and the signs this time are going to be negative for this. Our population is still a positive quantity. It's a positive number of creatures, animals, people. and k is going to be positive again, and this overall is going to be negative. And that means that p will decrease. And so if we start above the carrying capacity, then we're going to have some dying off in the population, because the environment cannot support the population that we've put into it. And again, that captures nicely what we mean by carrying capacity. If you're at the carrying capacity, you stay there. If you're below the carrying capacity, your population can grow. If you ever exceed the carrying capacity, then somehow it's not sustainable, and you're going to lead to a population decrease over time. This is a nice informal analysis that didn't actually require any integration to achieve it. So keep in mind that we will often do analysis just from the differential equation itself and not necessarily need to go through all the solving processes of separation of variables. What we get here is a little less specific. It's not as precise or quantitative as a solution, but it lets us do some reasonably good argument about what would happen under different scenarios without doing as much mathematical work.